All right, test 1, 2, 3. Just trying to test this and start about 10 minutes early. All right. All right. So today we're going to start in a minute. And All right, let me start this next section. If you look back here at, oops, somehow I got rid of the book. Okay, so if you look at what we were doing, okay, I'm going to have to bounce back and forth. We were looking at conservation of linear momentum for a system of particles. We went down through this and we realized we can basically have impact of 2 or more. And of course, if you look at this, this is a typical case in which you have the impact equation followed by conservation of energy to answer the actual problem. So we get down through here, and we'll go back and work a bunch of these, but I'm going to specifically address the homework in reverse. Now, let's start taking a look at this one. This is an impact and something that's interesting that occurs. And what occurs here is that if you take a basketball and drop it to the ground, and say you threw it in that direction, the path would look like this. Eventually, it would lose energy through the impacts. The impacts are going to lose energy along the way. So how does he deal with this? Okay. First of all, let's talk about the impact itself and not the loss of energy. You've got in 2-dimensional or 3-dimensional. Here he's showing it in 2D, but in 3D it's the same thing. There is a line of impact exactly where the impact, draw a line between the tangent of the 2 objects. This could be in 3D, but it's shown in 2D. Then he has something called the plane of impact. Now, obviously he's shown this as a line, but this is a plane actually. Something interesting occurs here. Along the line of impact, you're talking about using the impact equations. But along the plane, if there's no friction between them, there's no loss in that direction. So if we hit 2 balls together here, along the line of impact, there are 2 phases here. There's phase 1, where the 2 objects start and they deform. They reach a point. This is occurs at a delta t. The maximum deformation occurs at a time. It's not a delta t. It's instantaneous. And then there's a restitution phase, and this is another delta t, where they come back apart and then they go on their way. Now what he does is he goes down here and he says, hey, if we look at this and we consider this to be a system, there's no there are no external forces placed on either ball A or B during all of these phases. However, if I consider the system to be only A and only B, and think of it as being 2 systems, then I do have a force pushed on B by A and a force pushed on A by B. And you can see the signs are different, equal and opposite. So I don't know why he uses a P. The R makes sense. It's the restitution phase. But during the deformation phase, you have this. During the restitution phase, you have those 2. Essentially, the ball's coming back apart. Now, what he's done is he started with the system. This is the total system, meaning A and B together. Notice there's no external force. In other words, there's no F dt here. Now, let's consider only A. So what you see is that B is producing this. Now, this is for only A deformation, only A restitution. So here you go here, and this is the restitution phase. Then what you do is you say, hey, I want to know, come up with an actual term called the coefficient of restitution, and I'll put them in here like so. Okay, so it goes from state 1 to some state in which that is the t when it's maximum. This is the point in which the deformation is maximum. Same point. It's left here. Now what you do is you turn around and do it on B. You do the same set on B only, and you'll come up with this. Then you start saying, hey, wait a minute, let's look at the difference between these two, and you can put it together so that actually your coefficient of restitution looks like this equation. So now, and you do that by eliminating the V. There are two ways you can do this to eliminate the one is to set it up here. One is to set it up this way. Okay, VA1, oops, well, he had a parentheses here, minus EB is equal to B minus VA2. And then down here, EB, I'm taking this, moving it to the other side. This is kind of a mute point. Shoot. Anyway, so then you can go ahead and try to eliminate the V's out of here. There's two ways you could do that. Here, hang on. Minus V. Now, it's pretty ugly looking. But if you add these two, and I don't know what that little marker was there for. If you add these two, that kill each other by adding them, that is. And what you get is EVA1, this EVB1 is equal to B. That's a B, by the way. 2 minus VA2. And then you move them back out, and you'll see that this can give you this. Okay, so what happens is here's a tennis ball. Bounces, loses energy in the impact, doesn't return as high, loses a little bit more energy in the impact. And so what happens is this impact is taking energy away. You have two cases here and a lot of in-betweens. So you have a perfectly elastic if E is equal to 1. Completely plastic if E is equal to 0. So let's go ahead and work a problem here. Okay, so this is something you'll have to do on not just the homework, but on the final. Let me find a problem. As a matter of fact, let me just go after. Okay, so here's a good example in which what happens is you can see he goes in, he breaks down that into its X component and its Y component. Then he has a number and a number. He goes in, takes the VB, finds the X component and the Y component. And so he has two numbers here. Notice what he does. Next thing he does, conservation of the X momentum. Why the X momentum? Because it's the line of impact. So what he does, he does this. But notice what comes out of it. One equation, two unknowns. What's the other equation to help you? Here's your other equation. Somewhere in the problem, apparently, he said coefficient of restitution is 0.75, meaning you lost some energy in the impact. You take this equation, guess what you got? Here's your other equation. So you use equation 2 along with equation 1, two equations, two unknowns, you get a solution. Oh, well, he lists them as 1 and 2. So yeah. Okay, so conservation of Y momentum. The momentum of each disk is conserved in the Y in the Y plane, Y direction, plane of contact. Since the disks are smooth and there are no external impulses acting in this direction, then essentially you get this, which means cancel that, and the final and initial velocities are in that. Now, if you had friction, you would have to take care of that, but it would be a little bit more complicated. So let's solve this problem that I've given you here. Over on, oh, wait, it's right here. So I'm going to be working this thing backwards in a way. Okay. I'm going to take homework 12. Let's see. So the picture's the same here. The value the same. 6 and 4. 6 and 4. Okay. Let's do this one first, and then we're going to go down, and we're going to do this one. Pictures are the same, though. So here we go. Okay. All right. So first of all, it appears like this is the plane of contact. And this is the line of contact. So what I've got to do, I've got to list VA as a vector. This to be minus 6i. Then I have to list this as a vector, VB. And this is, I need to put initial equals to. Value of 4/5 going north. Well, let's do to the right. 4 times 3/5 I, that's the component going to the right, and then I got a component going north, which is 4 times 4/5 J. So here's my two initial. Now, let's do along the line of impact. Along the line of impact, you have MA VAX1 plus MB VBX1 equals to MA VAX final plus, that doesn't look like a 2, plus MB VBX2. Now, I don't remember the masses of these things. Each have a mass of a half. What's going on? Okay. So each of these has a half. So since they're all the same value, I can just cancel them all out. And then I can say, what is VAX1 minus 6 plus VBX1 4 times 3/5 equals to VAX2 plus VBX2. Pretty much it. So let me go ahead. 4 times 3 divided by 5 minus 6. Uh-oh. Shoot. What did I just do? I don't know. Am I right there? Okay. Try it again. 4 times 3 divided by 5 minus 6 minus 3.6 minus 0.6 is equal to VAX2 plus VBX2. There's one of my equations. That's one I'm going to have. Okay, so now let's move to this concept of coefficient of restitution. How can I remember this? Let me give you a tip. Okay, so here's the earth. Here's a tennis ball. Let's call this A, or let's call this B for ball. And we know it's VA and VB over, now what's funny, I remember it this way. I remember a swap here in the indices, but which one goes on top and which one goes on bottom? Well, here's what's funny. The ball is about to hit with a certain velocity. And let's make it this be positive. And then it's going to come off the wall at a slightly slower value. And the coefficient of restitution has to be between 0 and 1. Well, I know VB1 is equal to a negative number. Does that negative number go here? Does that negative number go here? But let's address the A first. Let's say the Earth is so big that in fact it didn't change its velocity at all because the tennis ball hit it. Because it is so massive. So now your coefficient is simply, coefficient of restitution is simply velocity of ball over the velocity of ball. If you're losing energy, then this one is going to be smaller. Since coefficient of restitution has to be between 0 and 1, then 1, if the tennis ball just hit the ground and stopped, it would be that. Meaning that this is the final state. This is the initial state. Let's look back the book and let's see how accurate that was. Okay, we're looking for 15. I probably have already gone past it. Okay, am I not seeing it? 7, 14. Okay. Wow. Okay, wait. What is wrong with me? Where is it? There it is. Okay. Okay. Notice this, okay? It's the final over the initial. So in fact, our assumption or our little mind game that we had here worked out. It's the final over the initial. So now let's use this. So this was a little tip that sometimes I use to make sure I can write the equation the way it should be written. So coefficient of restitution is this, but it only occurs along the x-axis because that's where the impact is actually occurring. So what I don't know VAX2 minus VBX2. I do know, this one. And I do know that one. So if I put this in here for 3/5 minus a minus 6. Now, I know he told me this is 0.75. So now I've got to just figure out what this is, multiply it times that. And so if you don't mind, I'm going to move this up the page and try to find that. 4 times 3 divided by 5 plus 6, 8.4. Oh, now I got to take that 8.4. So this is 8.4. I'm going to multiply it times 0.75. Okay. 8.4 times 0.75, 6.3. So what I get is an equation that says VAX2 minus VBX2 is equal to 6.3. There's my second equation. 2 equations, 2 unknowns. Now what I'm going to do with the magic of the lecture thing, what I'm going to do, well, now I can just do this. I can look up here and I can copy this equation down. VAX2 plus VBX2 is equal to minus 3.6. And I can add these 2 equations together. These 2 cancel. The other 2 do not. So I get 2A to VA. VAX2 equal to 2.3 minus 3.6. That's bizarre. Okay. 6.3 minus 3.6 is 2.7. Okay, so from that, I get 1.35 VAX2 is equal to 1.35, and the BX2, it just kind of depends on what you want to do. I don't know. Either equation should give me the same answer. I don't know. If I take this one per se, is equal to minus VAX2 minus 3.6, which would be minus 4.95. Okay, so what this is telling me, without, here, I tell you what, you can get the picture, copy it, get it back down here and zoom back in. So this tells me that, okay, so this is A. So A, so the B after impact, since this is coming at 6, this is going in slower, this thing is going to go off this direction. And after the impact, this A block, or this little ball A, is going to go to the left at 1.35. Now, there is a couple other things that is interesting, and that is this. Okay, let's look at the non-impact level. In other words, let's make a little spot. This is small. Here, this is the region we're gonna. So the impact along the Y, there isn't. So there is an impact there. So VAY2 equal to VAY1, which is equal to 0. There's no Y velocity there. Here, I'm going to turn on the secondary light in here. It's kind of dark, messing with my vision. There we go. That's a little bit better. My eyes will adjust. It'll be easier for me in a second. Plus, I probably could cut down the brightness of the screen on my end. You won't notice anything. Here. Is there a... Oh, yeah, that's why. The screen is super bright. Okay, that might be a little bit easier on my eyes. I don't think you'll notice anything. That'll be interesting to look. As a matter of fact, let me look at the lecture and see if there is anything you notice. Give me a second. I'm going to adjust the brightness and see if it affects the stream at all. Excuse me a second. Okay, you'll hear me in the background, but I want to see. Okay, let's try that again. Okay, so if I adjust the brightness, is there, it does this. No, that makes sense that it wouldn't do that. Here. Yeah, there's no effect. There's effect on my screen, but on the stream, you don't see. Okay, that's all I wanted to check. Now I'm going to cut you off and keep working back on the problem. Okay, but here's the thing. Initial velocity this way was 4 4/5. So the thing is, if there was no friction and nothing happened after the fact, that would be the same thing. So in other words, velocity b y2 is equal to velocity b y1 is equal to 4 times 4/5. So in effect, the velocity A at 2 would be just simply this, 1.35 I. Now, I did make a slight verbiage error here, and that is that I said that it continues to the left, but in fact it's positive, so I was wrong in what I was saying. It bounces off of this ball and goes back to the left at 1.35. Sorry about that. So there's your velocity answer for A. And that's what that is. Now, yeah, that looks pretty ugly. So here, let's do it that way. Let's look at what your answer for B is. Velocity of B is going to be 1. It's going to be this and the Y. But it's going to be this and the X minus 0.95 I plus. Let's see. Oh, the answer isn't here. The answer is back here. And the answer is not on this one. It is on that one, I think. Okay, so if I wrote the answer. Okay. So he says velocity A 1.35 to the right. He gives us velocity B this way. Let's see if we can get this out of our answer. So what we got, velocity B was minus something. What was it? Minus 4.95. 4.95 I plus, and instead of entering this, let's see if we can figure out what that is. 4 times 4, 3.2. 3.2 J. So the magnitude, so if we drew this vector, here's your X, here's your Y. Draw a vector that goes back about 4.95 and then up about 3.2. So here's your velocity vector. So that velocity vector's magnitude would be square root of 4.95 squared plus 3.2 squared. Okay, we have our handy dandy, extra handy square root of 4.95 squared plus 3.2 squared. 5.89. 5.89, or was it 9.8? I think it was 8.9. It was 8.9. So that's what we got there. Now 32 degrees, where did that come from? Well, he's saying that's measured up from here. Well, there's two ways you could do that. I like to stick, when I can, with cosine is inverse of 4.95 over 5.89. Now let's see. Here we go. Oh, what am I thinking? I'll put it right here. Okay. 4.95 divided by 5.89. 32.81 degrees. So 32.81 degrees. I like my answer a little bit better than his, but probably if I add more digits, I would have got it. But now what's he saying here? If the both disks are moving with the velocity shown when they collide, determine the coefficient if after the collision travels along the line 30 degrees counterclockwise from the y-axis. So this means after the collision, well, yeah, that doesn't look like 30 degrees. After the collision, this is 30 degrees. Well, I know before impact, here, this is 3.2. That's what we figured up. In other words, this number 4 or 16 over 5 is 3.2. If that's 3.2, hang on, and this is 30 degrees, and what is this, and what is that? First of all, I'll find the magnitude. So the cosine of 30 degrees is going to be equal to this distance. So really, actually, I think I better do the sine. Sine of 30 degrees is equal to 3.2 over the velocity b magnitude at 0.2. So velocity b magnitude is going to be 6.4. Is that true? Let's find out. Sine degree of 30 times, no. Okay, wait a minute. 3, okay, that value is a half. So this will be a half, 1 over 2. So this means if you take this equation, then yes, in fact, that's the case. So if that's the case, that this velocity b is 6.4, then what's the cosine of 30 degrees? Well, it's equal to the b x, or bx 2 over 6.4, and vbx2 would be not visible here. Okay. 6.4 times cosine degree of 30 gives you 5.5426. 6. Okay, now that you have this, look back at your equation and you'll see something interesting. Now, to do this, I'm going to go back here. Okay, what was not known here? Okay, so if you look at this equation, this is still in force. It's fine. So what I'm going to do is I'm going to slide to the right, and I'm going to say BAX2 plus BBX2 equals to minus 3.6. Now, if I take this equation, I have something interesting. So again, this on the bottom is the initial. It did not change. However, this is 8.4. However, now the new equation is this. B, I'm taking this. Okay, so let's think about this. Taking this equation, now I do not know E, but I take this 8.4 and multiply it times E. So say equal to. Now what happens over here? VA2X and VBX2. I know that one. That's the final velocity of the block, of the, I say block, but ball 2, ball B. That was 5.5426. No, wrong thing. Hmm. .54. Let's just do it. And it's minus because it's going back to the left. So this would be plus 5.54. And this would be VAX2. Well, wait a minute. If I know that's the case, I can take this out and put that in 5.54. I might get slight shifts. Now, the only thing I have to deal with is this. We got two equations individually. One from the coefficient of restitution, one from the momentum, and that's where I'm at. So I guess I'll subtract this equation. Now I'll put a minus in front of it, add it, I get, okay, I'm going to have to, all right, well, yeah. Where's my, this is it, 5, wait. I can just do an arrow up. Multiply times 2, 11.085 is equal to 3.6, 8.4e. Take the 3 over 1.085 minus 3.6 divided by 8.4 equal to a number. And that number is just going to be E is equal to, so if you'll bear with me for a minute, 11, wait. I have that up here. Parentheses, all of it in minus 3.6 divided by 8.4. Still the lights in here, 0.89. Is that what he got? It's probably not. Ooh. I seriously doubt this answer. That is the coefficient of restitution? No, that can't be. There is one. Let's look at this. So it's 0.75 at 32 degrees. And what we're saying, no way. That's not correct. I don't think that's correct. Here's why. Okay, well, I should look at, here's why next time. We're going to look, next time we're going to go into this problem. Okay, so here's what we're going to do next time. I'm going to take this problem and I'm going to investigate two items. One, okay, good. And we'll see. I think I can see what's going on here. What's my two items? I'm going to look for E is equal to 0. I'm going to look at that one, and E is equal to 1, and what happens there. And what we're going to do next time is we're going to look at these two specific cases for, in fact, this problem. What we'll find out is kind of eye-opening as far as each one of these. And then on that front, I think I will disprove this. I don't believe that at all. We'll look at that, and I'll see if I can, we'll deal with that next time.